Welcome back, witchlings, to another installment in my climate change series. Previously, we compared anthropogenic and volcanic carbon emissions through the use of the Delta 13C carbon ratio. Today we'll be attempting to critically examine why a snowball on the Senate floor doesn't hold water as a retort to climate change. What happened on the United States Senate floor on February 26, 2015 was a display of the difference between weather and climate, and to be honest, it was a really bad one at that. Weather is the here and now, or the present state of the atmosphere in a particular region. It takes into account things like humidity, temperature, and wind speed. Generally, when we talk about the weather, we're referring to a local or regional level. It only applies up to a certain point until we're actually incorrectly referring to climate while using the word weather. Additionally, weather is highly time-dependent. As the joke is in Texas, if you don't like the weather, wait an hour. Relative to the history of the Earth, we are talking about extremely small increments of time, such as hours, days, sometimes months or years. If there's one thing we all know, it's that weather people aren't very good at predicting what's going to happen in those increments of time. Why is that, though? This actually has a great amount to do with chaos theory. That is a branch of mathematics in which systems are examined, like our weather, that are highly dependent on and sensitive to the initial conditions. This can be seen in the mathematical equations used to describe these systems, but we'll get to that in a moment. One may have heard of the adage that a butterfly flapping its wings in Brazil can cause a tornado in Texas, and that isn't too far from the truth. Fluids like air are dynamic systems whose physical properties are highly sensitive to disturbances. This can be seen in the mathematical models for such systems that use a group of equations known as nonlinear ordinary differential equations. These equations relate some function with its derivative. The function tells you the physical property, the derivative tells you the rate of change of this physical property, and the entire equation tells you how these things are related to one another. For weather, we simply can't keep track of all the atmospheric disturbances that could change the day, week, or month's weather. A new plane flying overhead in a region could induce a hailstorm a week later. That's just how complicated it is. There are too many variables to keep track of. This was first discovered in the 60s by Edward Lorenz, a mathematician and meteorologist from MIT, who wanted to make a mathematical model of the weather. He was able to condense his work down to 12 differential equations, which amounted to a crude oversimplification of the true state of nature's mathematical prowess. During a lazy yet extremely productive day in Lorenz's life, he wanted to re-examine a sequence of data, but didn't want to start the entire data run over again. So instead, he entered the data for about a quarter of the way through. Thus, he had changed the initial conditions of his model. As the computer tackled plotting these points, an unexpected deviation occurred. All human understanding at the time would have indicated that after a certain point, the data would match up perfectly. Although he didn't know it at the time and assumed that his computer was malfunctioning, what he just observed would go on to change the understanding that we had of these mathematical models, as well as the weather. This is because, in general, When we think of small changes to a system, we think of a proportional response. However, in changing these initial conditions just a little bit, it wasn't by much. It resulted in wild and dramatic fluctuations and changes that would be predicted. While we can't use this data to predict the future of the weather, it's still valuable to keep and examine. Because if we use it for something else, the more of it we have, the less our error is. So we keep all the information about townships, counties, states, and nations, so that we may feed that data to other statistical methods within our toolbox. We can't increase our scope too much either, because we will run into the same problem that weather has, in that there are too many variables to account for. That is why, as we discussed in our epic talk, we only examine the last 800,000 years when we're talking about this climate changing. That particular subsection of time tells us what we should be expecting today, because it controls for variables like ocean current circulation, terrestrial and atmospheric composition, as well as many other factors. Once we've made sure that we're not comparing apples to oranges, we can look at the average values for certain things, such as CO2 concentration in the atmosphere, for example. We could examine the changes in the atmosphere in a child's lifetime, or the change in the climate over a few generations. Generally, of course, we examine from the Industrial Revolution to present, as well as the last epic change to the present. The latter tells us exactly what we should expect the atmosphere to look like without industrialization, while the former tells us what it looks like in the current state with industrialization. If you've kept up with the other videos, then you already know the impacts that humans have made on their environment even before fossil fuels. Thankfully, as you can see, we don't have to predict the weather in order to understand our climate. We just need to collect data through various techniques such as ice core sampling, soil sampling, and tree coring, as well as many more methods. We will continue to have a global impact as long as we continue down this path, and to be honest, we'll have an impact anyway, but at least it won't kill us, and at least it won't kill many other species, and we'll get to the mass extinction at a later point in time. What we do know is what these particular changes can result in, but we aren't too good at predicting what might happen in the future, which a lot of people have a problem with. Yet that is another example of chaos at work, because certain factors may change. You see, no one can say exactly what new technologies may arise for carbon sequestration. We don't know exactly how much emissions will be reduced, and we can't predict shifts in global thinking that change the course of history. We can only say what's happening in the present, as well as what should be happening. Thank you so much for tuning in, witchlings. I appreciate your love and support. You are all so very wonderful, and I hope that you stay safe, because you are incredible. Bye.